memorize. Otherwise, you need time to study. And then when you create the circuit, you can remember. Again, what is the definition? 1 qubit. 0 becomes 0. This is 1 qubit, right? So how many basis states does it have? 2, right? Only 0. I only look at 0 and 1. And 1 becomes what? Becomes e to the power I phi 1. So what does it do verbally? For the 0 vector, you keep it unchanged. For the 1, what does it do? Add a phase in front of it. A complex number in front of it. Just add a phase. And you can see that this is very important because I told you at the very beginning, the phase is very important. We use for constructive and destructive interference. And this can be used for many calculations, the phase. That's it. Have a phase. The vector is rotated by adding a phase, which is not really rotated, right? Just have a phase. Definition. So how can I write it in a more I don't want to actually. Just write the matrix. By the way, I did not ask you. Is a 1 bit, the matrix is going to be what size when you have 1 qubit? What is the size of the matrix? 2 by 2, right? Because you have how many basis states? You have 2, right? So just now we have 4 by 4 because it's 2 qubit, right? You have 3 qubit gate. How many do you have? 8 by 8, yeah. So you use this to check. The matrix is this. 1, 0, 0, e to the power I phi. That is easy, right? Let me just check. I am going to check only the 1. Apply it to 1, 0, 0, e to the I phi. Apply on 1, which is 0, 1. Then the top is still 0. The bottom is I, ei phi, right? I can take it out, becomes ei phi, 0, 1. So this is ei phi, 1. As expected. Right? That is the definition. A very simple matrix. Now this is so simple but very important. Why? When the phi equal to pi, what is it? When phi equal to pi, this is 1, 0, 0, e to the power I pi, right? You might forgot, but can you tell me, let's remind us, what is e to the power I theta? Cosine, cos what? Theta plus pi sine. Very good. So when it is pi, what is this? Thank you. What is this matrix? Sigma c. Okay, so that's what phase shift. Today we just learned the log gate, right? Which correspond to the sigma x. Did I mention this? This is just sigma x, right? Log gate is sigma x. Phase shift gate with pi equal to with phi equal to pi is sigma c. Okay? So finally, give me 1 more minute, right? Let me tell you something. If I apply sigma c to the plus state, phase shift gate, it is equal to sigma c to what? What is plus? Do you remember? 0 plus 1, right? So this is equal to 1, 0, 0, negative 1, 1 over square root 2, 1, 1, because we're working in the 0, 1 basis. This is equal to 1 over square root 2, 1, and then minus 1, which is equal to what? Minus states. So you see that the plus becomes minus. What gate is this? Not gate. So sigma c is the not gate in plus minus basis. Just like the NOT gate, which is the sigma x in the plus minus basis, that gate is the NOT gate in the 0-1 basis. Think about this, maybe we talk about that again later, right? But, okay, let's stop here. About 2-qubit phase shift gate. So it's a control phase shift gate, right? So first, let's define it. Define what is a 2-bit phase shift gate. Again, as I said, always define it by telling how it rotates the basis vector. The definition is this. There are 4 basis vector, right, for 2-qubit. What are they? 0, 0, let's do one by one. 0, 0. In the definition, it is still 0, 0. Okay, what is another one? 0, 1, thank you. In the definition, is still 0, 1. The other one is 1, 0, thank you. 1, 0. In the definition, is still unchanged. Okay, in this control phase shift gate. How about for 1, 1, the last one? It becomes e to the power I phi 1, 1. Okay, so for all the basis states, it doesn't change, except that for 1, 1, it adds a phase in front of it. So how do I describe this one? I can describe it by using this equation. I say this phase shift gauge, control phase shift gauge phi, apply to AB. Now you know very well what is the meaning of AB, right? What are A and B? The number labeling the basis state, right? So what can be the value of A and B in this case? 0 or 1, right? Equals to e to the power I A dot B phi AB. That you can make this definition. It helps you to derive equations. What is A dot B in this case? Be very careful, right? From now on, be very careful for each definition. Look carefully what it means. Here it means A and B, where this is a classical AND. Okay, just a classical Boolean AND. So under what situation? What is 0 dot 0 then? 0, 0 dot 1, 0, 1 dot 0, 0, 1 dot 1, 1. So you clearly see that if this is e to the power 0, that is 1, right? So you only have effect if A dot B equal to 1. It means only when A equal to B equal to 1. Means you only change when it is 1, 1, right? So this is easy. For example, right, just to show our definition, 1, 1 equals to e to the power I 1 dot 1 phi 1, 1, which is 0 e to the power I phi 1, 1, which is exactly what we define here. Okay, so that is the definition. I hope you understand. Is that okay?
Question.
Yeah.
So now if we transition from a 0-1 basis to a plus minus, this phase shift gate, would this become a controllable One-qubit?
It is. We can play with that later. It will be easier to see if we look into the matrix form. Yeah. Okay, so how do we write in the matrix form? We will do it at the end. I did not plan to do it, but since you asked me, let's try. I can see if I can do it, right? So this is the matrix form. Or actually, can you guess now? Let me don't write here. Can you guess now what is the matrix form for this guy? Is it first, what is the size of the matrix? 4 by 4, because it's 2 qubit, right? 2 to the power 2, right? I have 4 basis state, right? Good, very good. So At least now I know that UPS, not the parcel not the delivery company, equals to, you say 4 by 4. Good. Now, based on this, can you guess, right? You can guess, right? That's how how would it look like, the matrix? 1 0 1 0 0 0, and then 0 1 0 0, and then I5. Yes, you're right. That is how you define it. So in general, right? The vector psi can be equal to alpha 0 0 plus beta 0 1 plus gamma 1 0 plus delta 1 1. How do I write in the column form? Alpha, beta, delta, no, gamma delta, right? Gamma delta. I hope you can recognize that. What is the meaning, right? It means you have alpha component of 0 0, beta component of 0 1, gamma component of 1 0, delta component of 1 1. Everything is the same as the 1-qubit case. You just need to recognize what are the basis state carefully. Mark that. And this might be the reason why he was able to derive this one. Because he recognized that this matrix is talking about how I rotate the 1 1 state. If I want the 1 1 state to be, 0 0 state. If I want 0 0 state to be intact, it must be 0 0 1 0 0 0. Because 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 EI5 times alpha, beta, gamma, delta equals to what? The first row times the column, right? Nothing changed, alpha. Second row times this column, beta. And then similarly, gamma. But the last one is going to be EI5 delta. Right? A little bit messy. Very messy, right? But it's very clear. So, question? Okay, yeah. So someone doesn't like my notation. He want me to put CPS. I'll just say put PS here because okay, let me put CPS. I don't have a standard notation here. But thank you. Maybe I put CPS is better because in the 1-bit shift gates, I did not put anything. Yeah, but to my book, right, I put CPS. Thank you. Is that okay? Now, let me ask you what this is called control rotation. Can someone come with an explanation why this is a control rotation? Why we call it not control phase shift? Based on the definition. It only rotates the phase if the state vector, right? So can we be more specific which one is one? I'm talking about control. Control phase shift. When the control qubit is one. Which one is the control qubit? The MSB, right? The most significant bit, right? So let me say this, right? I'm going to copy it one more time. This I call control phase shift, okay? Equal to 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 right? Or actually, I should even just write down this notation, this definition, that will be easier to see. UCPS AB equals to e to the power I A dot B phi AB, right? If A equals 0, remember A is what? The controlling qubit. Okay? And B is the target qubit. Just like the control knot, controlling and target, right? If controlling qubit is 0, A dot B is always equal to 0. No matter what, you don't do anything, right? Nothing. Then, but if A equal to 1, then A dot B equal to what? Equal to B, right? It depends on B. So it's just equivalent to applying a phase shift gate to the target bit. Remember this phase shift gate. You don't always apply this phase shift. You only apply if your value is 1, right? So same here. Well, first, your controlling qubit need to be 1. After that, then depends on B. If you are 0, we don't have any phase shift, but if you're 1, then we apply the phase shift, right? So it says equivalent applying the phase shift gates, but phase shift gates still need to look at this B. Is this okay? So that's why the symbol is like this. Right? There can be other symbol, right? It's not standardized. This is the phase shift gate, right? So this is the controlling qubit, and this is the target qubit. Okay, and then you have this psi comes in, alpha, beta, gamma, delta, and then your output is going to CPS, not CPS, I mean, we don't need CPS. The output is just alpha, beta, gamma, e to the I phi delta. Is this okay? Now, so I want to take this opportunity to talk about the MSB and LSB. MSB refers to the most significant bit. Is this okay? It means the bit on the left. Oh no, depends. If it is a little endian, it's the bit on the left, right? We will just keep this. Okay, in our class, the bit on the left is the MSB. LSB is the least SB. Okay, least significant, the bit on the right. So do you see that on the figure I'm drawing on the left, which one is the MSB? The top or the bottom? Yeah, because the top is controlling qubit, right? Now, you can also draw it in this way. It really doesn't matter. This is still alpha, beta, gamma, delta. Okay? But you need to tell people this is MSB, this is LSB. And this is the circuit you will see in IBM-Q. Now, there are some more complications related to the big endians and little endian, right? Let's ignore that. In our class, it's all little endian, okay? So, but the problem is sometimes people draw the circuit in this way. using this, you just need to be careful, right? So when you draw the circuit, now you need to remind yourself whether it's MSB or LSB. So if any questions?